All right, well, we are going to go ahead and get started. Welcome back to How to Build a Cloud Data Platform, Part 3, keeping data up to date with structured streaming, managed data for GDPR compliance. A few housekeeping items before we begin. If for some reason you did not receive the on-demand links for day 1 and 2, we will drop them into the chat. Please grab the links from the chat and use them. It'll be the best way to access the on-demand videos, as well as the coupon code for, or the link to get the Databricks Academy class for free. We will drop all 3 of those links in. Please use those links going forward. We will also have live Q&A at the end of this session. Doug also will be answering questions throughout, so please use the Q&A function to ask your questions. We will have a survey post the series completion in the next week or 2. So please fill out the survey when it comes. Let us know how you found this and what content you would like to see going forward. As a reminder, this will be the same Zoom link to access tomorrow's session as well. And with that, Doug Bateman, lead instructor at Databricks, will take it away.
How to build a cloud data platform. So welcome back to part 3 of our 4-part series, how to build a cloud big data platform for BI and ML. And this is part 3, where we will talk about how to keep data up to date with structured streaming. So we have our tables. How do we keep those tables up to date as the data changes? And then as well, how do we manage and groom those tables, for example, to clear information necessary to comply with European General Data Protection Regulations for privacy? So with that in mind, I'm your instructor. My name is Doug Bateman. I'm a principal instructor here at Databricks. I've been with Databricks for 4 years, and I have roughly 20+ years of experience designing and architecting applications. As I mentioned, this is part of a 4-part series. We're now in part 3. So if you are watching this recording and you've not watched parts 1 and 2, you are certainly encouraged, but we also try to make sure that if necessary, you can jump in at any point and just start watching where you're at. And for those who would like to access the course materials are available at academy.databricks.com. This link will take you directly to the materials that I'm using so that you can do this training on your own and really free up us to do Q&A and discussion and dive deeper during this presentation. So if you are following that link, you'll be taken to this page here, how to build a big data platform, where you can enroll for the contents of this training series for free and do these exercises on your own after the training is over. We ask that you not share this link with people who have not attended the webinar. It's a special treat. Normally these trainings cost a little bit more at academy.databricks.com, but if you come to this link through the webinar, you are able to get these particular courses available for free. And once you've signed up, you'll go to a page here where you're going to be able to see the courses. On Seminar 1, we worked with Fundamentals of Delta Lake. On Seminars 2 and 3, we're working with Delta Lake Rapid Start with Spark SQL. And we had a few cases where I built out some notebooks separate from the seminars or separate from the course material. And we've made those notebooks now available as a 3rd course where you would simply download those notebooks and import them into Databricks Community Edition. So with Databricks Community Edition, you just go to databricks.com and click on Try Databricks, and you're able to sign up for a free account at Databricks Community Edition, and you can start using Databricks right then and there. So with that in mind, let's do a short review of what we've covered so far. So first of all, just a little background on Databricks. The goal of Databricks is really to create a unified platform, what we call unified analytics, to make it really easy for people to unify data science, engineering, and business to really extract insights from your data. And we are also the original creators of Apache Spark, Delta Lake, and MLflow. We always like to caveat the word original because at this point, these platforms have taken on a life of their own. They're large open source projects with contributors around the world. And what we do at Databricks is we create a hosted version of these platforms, and we add a lot of secret sauce to really make these platforms run well in the cloud and accelerate delivery of your solutions. So instead of having to stand up your own copies of Databricks, or excuse me, of Apache Spark and MLflow and Delta Lake, you're able to do it on Databricks and have it tuned and optimized and run really effectively in the cloud. And there's over 2,000 companies worldwide that are now using our platform to do their big data and machine learning. And so what does that look like? This is kind of a picture of how we are looking at using Databricks. We have our various operational data stores. Oops. Try that again. There we go. We have our various operational data stores. These represent any databases that are capturing the current state of the data or the original sources themselves. So it could be a snapshot taken from an external system, or it could be the external system itself. And we want to ETL that data into Databricks, or really into our data lake. And our data lake is just going to be open source file format. It could be using JSON files, or it could be using Databricks Delta. And we'll store it out in cheap, abundant cloud storage. So something like Amazon S3 or Azure Data Lake Storage or Azure Blob Store. And we make this data available using Spark. We write it out in this open source format. And then when we want to query it, we're again able to use Spark running on Databricks. So end users use our notebook experience inside of Databricks or integrations with tools like Tableau. And then they're able to query this large volume of data. And what a data lake makes available is this huge scalability. And I'm able to just store lots and lots of data and extract insights from it later. And extracting insights from a data lake requires that we deal with the data cleanliness problem. So the first goal is just to capture the data from the external systems. And that's what we call our bronze layer, or our loading layer of our system, our ingest layer. We simply extract data from these other systems as much as possible, and we store it in our data lake. And we don't worry about cleaning it initially. And this overcomes one of the big challenges of a data warehouse, which is cleaning your data. One of the big challenges of a data warehouse is that cleaning your data becomes such an arduous process that people are reluctant to even load their data into the data warehouse. And then when you need the data later, it's just not available. So our philosophy is grab the data, store it in this cheap, abundant cloud storage, and then when you need it later, you can always clean it. And so that's where the silver tables come in. You find, yes, I do want this section of the data, but that section of the data hasn't been cleaned. It might have erroneous records, or it might not be in a queryable format because it's in JSON and hierarchical, and I want to flatten it out to make it easier to write SQL queries. Or perhaps I've got bad data records that I need to correct. So the goal of the silver tables is to create a higher level of data quality. So this is really where you're building what would be your traditional data warehouse, but rather than using a traditional data warehouse product, we can use cheap, affordable data lake storage to construct these tables by using Apache Spark. So we're going to read from these bronze tables and write into these silver tables. And we're cleaning the data as we go. And we only need to make silver tables for the data that we're actually interested in. So this may be a subset of all the data available. And that overcomes that overhead that we have with data warehouses, where people had to do a lot of cleaning up front. Here we do cleaning almost just in time. When I discover I want the data, I add that to my higher data quality tables. And then eventually we get to the point where we want to construct data marts that are useful for AI and reporting. So I may be generating tables that are going to be used for business intelligence applications like Tableau, or I may be generating tables that can be used as features for an AI pipeline. So I'll do feature extraction out of these silver tables to create my gold tables that can be read into my AI pipeline. And these gold tables in turn are the ones that are really intended to be primarily used by consumers. So we give up worrying about normalization at this point. We're doing aggregations and rollups, and bringing the data one step closer to how a given family of users or a department of users needs the data to look. And what you'll notice here is that this data is therefore derived. The silver tables are derived from the bronze tables. And the gold tables, in turn, are derived from the silver tables. So this poses an interesting question. What do we do when new data is added to the bronze layer? How do I update those silver and gold tables? In a traditional product, we might use something like a materialized view, but how do we do that in our data warehouse? And or in our data lake, I should say. In our data lake, in a cloud data platform, we're going to use structured streaming to look at what's new and to update our downstream tables. And so that will be one of the big focuses of today. We'll be creating this pipeline where I read from one family of tables to write these downstream tables and keep them up to date as new records arrive at the bronze layer. So in the previous seminar, we also talked about some of the data manipulation language, and you'll notice this looks a lot like regular SQL. So this is one of the big goals. We should be able to use regular SQL to work with our cloud data platform. So even though we're not actually in a database, we're just using Spark to manipulate table storage that's out on S3 or Azure Blob Store. We want to be able to use regular SQL to do it. And this is something that Delta Lakes really makes available, is the ability to be doing updates to our tables and changing our tables. And that's because Delta Lakes adds to our file format the ability to have a transaction log that will track updates and allow concurrent updates to tables that don't conflict with each other. So we have, for example, insert into Health Tracker Silver, this new set of data from newly arrived records. And similarly, we could do merges. Merge performs what's known as an upsert. So we say, if the data is already there, we want to do an update. And I think I deleted a line. There should be a if matched, then update. And I think when I copied it into the slide, I lost the word update here. But that's okay. You're going to update and then set. I'll just add it now. Set health tracker heart rate equals upsert's heart rate. Or we could actually go to the notebooks that we used in the last class session and see what that looks like. So here we go. Update set was the missing line. When matched, update set, and we can change the record. When it's not matched, then we can insert the record. And so the idea of merge is that I'm able to do batch updates and batch inserts into an existing table in a highly efficient format. And this is really important because we are doing bulk updates. One of the really important distinctions of a cloud data platform is that it's not a transactional database. So we're not trying to just update one or two records. What we're really trying to do is get batches of records that are changed because we're updating our warehouse with the latest data from those operational data storages. So the operational data storage may be more transactional, designed to update individual rows, but we're then going to do these batch updates to update our data warehouse for query purposes. So it's optimized for queries versus updates. And this is why doing batch updates with merge is so important. And then we also talk a little bit about how to get the history for our table. So one of the cool features of Delta Lakes is that we're able to actually see previous versions of a table. So we can use the describe history command. So going over to the notebooks that we had from the last session, describe history, and I could see version 0, version 1, version 2, version 3 of a table, and what changed, and get information. I could even see how did it change? It changed as a result of a change by this notebook. And who changed it? Who was the Databricks user who changed it at that time, which is really nice. They get this audit history of my table. And not only do I get an audit history, but I'm able to go back in time and view previous versions of my table. So example of that would be to go select star from health history server version as of 1. Let's see, I'm at version 2 right now. I go back to version 1 and I can see a prior version of that table. And the reason that works is that when Spark is doing these updates that we saw, it's really updating files in our Azure Data Lake store. So version 1 might be represented by these 3 files. And then when I go to do an upsert, so I'm doing a merge statement, I might be updating this file. So I write out a new version of file 2, and maybe I'm appending another file as well. So I mark this file as old, and I write a new version of that file out to disk. And then maybe some new data that I've written out adds to another file. So now I have these 4 files on disk. And if I wanted to access the earlier version of the table, all I need to do is to read these 3 files, the original files, as opposed to the new files. And I'm able to access previous versions of the table. This also has the benefit of allowing people to be running queries on the old versions of the table while we're busy writing new versions of the table. So while somebody's busy doing a long-running nightly job that's creating the updated version of our data warehouse, other people can be running queries on the existing version of the data warehouse, which is really, really nice. And if something was to go wrong in my job while I'm busy writing out version 3, no problem. I just don't activate these new files, and I don't deactivate this file, and I stick with the previous version. So I'm able to roll back an operation if necessary. And so this is what Delta adds on top of the existing file formats like Parquet and our data lake. We're able to get some of these services that are expected of a data warehouse, but we're able to do it on our data lake platform. And this is huge because we get the scalability and ease of a data lake, while at the same time getting a lot of those guarantees and capabilities that a data warehouse solution would have. And this union of a data lake and a data warehouse is this vision we call a lakehouse. And Databricks is really committed to this vision, and over the next several years, we're going to be adding even more to support this. But what we are showing you today are things you can do right now in the product, which is really, really cool. Oops. There we go. So we're able to see history. The other thing that was worth mentioning is this optimize command. So optimize says sometimes when you do a lot of updates, let's say I've been doing a ton of updates to my table, I end up with a lot of small files. Every time I do an update, I'm adding more and more files to my table. And this can get to the point where there's so many small files that it slows down your query performance. So one of the features of Delta is this optimize command. And what it's going to do is simply group small files into a smaller number of big files. So I'll take all these small files and I'll target a file that's roughly 1 gigabyte in size. That's our target size. So we take a lot of small files and we build out these fewer, bigger files in our Delta Lake. And what we're doing is just making another version of our data. So while I'm busy compactifying these files, people can still be running queries on the older versions of this data, the older files. But eventually I get to the point where I've got more efficient large files, and this greatly reduces my query time. And then the challenge becomes, what do I do to get rid of these small files over time? So if I'm not interested in the older versions of the table anymore, we have the ability to vacuum out older versions of the table. And by default, when you run the vacuum command, it will vacuum out files that are older than 1 week. That way we know with high confidence that any jobs that we're running and reading the old version of the files have finished. But you can change that vacuum period to be older or younger than that. And that helps clear out older versions of the files. So this was the optimize command, and it's one of the things that makes Delta screamingly fast compared to a file format like Parquet. So we're going to save the questions slide for a little bit later. Actually, that's not true. There were a few questions from the last seminar that I wanted to come back and touch on. So one of the questions that I thought was really good is he said, hey, can I use this with Azure Data Factory? So I went after the seminar and did a search. There is a blog post here that talks about using Delta with Azure Data Factory. So I thought that was a really great question. I also checked with the engineers, and it seems that we are in the process of adding new features right now that are not quite released that will make it even easier for Azure Data Factory to read the Delta file format. But you can see the current state of things from this March 6th blog post at Databricks. And I wanted to make sure that I had a correction of my earlier answer that the features for reading Delta in Azure Data Factory are being actively worked on and improved as we speak. So there's partial support right now, and there'll be more support over time. And if you'd like to learn more about that, go and check out this blog post about using Delta with Azure Data Factory. There were a couple of other good questions we got. For example, somebody had noticed that we partitioned our columns in our Delta table. So if we go back to our example from before, let's see where we did partition by. There we go. No, that's not it. Where did we do it? When we first created our Delta table. Here we go. It was a parquet table, partitioned by, and we partitioned by, in this case, the device ID. So what exactly is it doing when we partition a file? So if we partition a file in our Delta Lake, what's happening? So we're going to drop down to the file system level and take a look in that directory. And you see that basically my files have been split up into multiple directories, one for each device in this case. And then if I go inside of that devices directory, you'll see the individual data files that are associated with it. And in this case, you see quite a few because I haven't vacuumed up the older files yet. Now, what this means is that if I'm running a query, select star from Health Tracker Silver, where P device ID is only 0, I don't need to read any files other than the files that are in the directory for device 0. So I've reduced the amount of data that I need to read from disk because I'm only querying 1 or 2 partitions of my data. So partitioning really speeds things up if I'm only interested in a subset of the data. However, it also can slow things down if I'm reading all of the data, because at this point, I have more files to read. I have a minimum of 5 files, 1 for each device. And what we had seen is at some point, each of those directories had 200 files in them. So that meant I had to read 1,000 files to process my big query. And the example from that was when I did version as of 2. We notice that it runs a little bit slower because it's having to read 1,000 files. So partitioning is a double-edged sword. It makes it faster when I'm only interested in a subset of the data. There it is. It took a full 12 seconds to read 1,000 files, which is pretty good when you think about it. But there's a cost to partitioning. It speeds up when I'm interested in a subset of the data, but it slows down when I'm interested in all of the data. Now, one of the cool features that Delta Lake makes available is an alternative, and it's called Z-order. Rather than partitioning by device ID, instead of putting each device ID in their own directory, we could say instead, put device IDs together into the same files, but you might be allowed to have 3 or 4 devices in the same file. So this is an alternative to partitioning, and it's really useful when the data is not like when you've got lots and lots of device IDs. If I only have 5, it's not a big deal, but let's imagine I had 20,000 unique device IDs. Well, that would mean I have 20,000 subdirectories, each with a set of files inside of it, and it would get unwieldy really fast. So in that case, partitioning by device ID that's got a huge number of distinct values would be a bad idea. But if I Z-order by device ID, instead of having 10,000 different directories, I might only have 5 files, but some of the devices would be in this file. Some of the devices might be in this file. Very poor drawing. You'll have to forgive me. Some of the devices might be in this file and so on, so that if I'm querying for a specific device ID, I only need to read the files that have information about that device ID. So it's an alternative to partitioning, and it works really, really well when I am only interested in a subset of the data and I've got lots of unique values. And this is a feature that's added to Delta on Databricks, and it is really, really powerful. And so then the question became, well, when should I partition and when shouldn't I? Well, we do have some general rules of thumb. If you're going to have a partition, so you go back to the code over here where we really did partition by something, we like to say that each partition should be roughly 10 gigabytes in size. Not smaller than that in any case. So and you should have a small number of the things that you're partitioning on. So, you don't want to have more than 100 or so, maybe 1,000 partitions, depending on the size of your data. One of the biggest performance killers is over partitioning your data. So when in doubt, don't partition. But if you've really got a clear case where, yes, I'm only interested in subsets of the data and I'd like to organize them into separate directories, that's where partitioning can become really useful. But a good way to know whether it's appropriate is that each of your partitions will be at least 10 gigabytes in size. Smaller than that, consider Z-ordering instead. So that was another question that we had from the last session here. Somebody else asked, is Databricks Community Edition free? And the answer to that is yes. Databricks Community Edition is a stripped down subset of features, and it runs on a 2-core computer in the cloud. So it doesn't scale out. It's you get your own dedicated 2-core machine for a period of time. You get a subset of the Databricks features. And the idea is that you could use it for learning and doing these types of labs and trainings that we're doing here in this webinar. And then when you want to scale out for a real project, you would come to Databricks and get the full version of Databricks at that point. All right, so let's go ahead now and continue on with our review of yesterday. So let's see here. When we continue on with our review of yesterday, we're working on building out this pipeline with the Internet of Things. And let's find our slides. Here we go. We had just finished doing a merge operation. So if we go back to our code, scroll down to the bottom of our notebook from yesterday, you see that we had just done a merge operation where we fixed broken records and we inserted new records. So we fixed the broken records and we inserted new records at the same time with our merge operation. And it turns out that while we fixed those broken records, when we inserted new records, we inserted new broken ones. So let's do this query here to see if there's any broken readings. So let's just do select our count star first from broken readings. Select how many broken readings do we have? We have 3 broken readings. So it went down quite a bit, but we had inserted 3 more broken records, which is really unfortunate. So we need to do something to fix those broken records that we had just inserted. And the reason we're demonstrating this is because it is not at all unusual that over time you're going to continue to find things that are broken in your data. So the fact that we inserted more broken records is really more for narrative value than anything else. It's to let us have an opportunity to see exactly how this would look if we were trying to do these types of fixes afterwards. So it just happens to feed into the narrative of where we're trying to showcase the power of the platform with our demo, that we inserted more broken records. So let's come back now and verify that these broken records are in fact broken. So let's look at anything that's older than our previous date. So let's make sure that these are in fact only new records that are broken. So I'll come in here and I'll run this query, select some broken readings count where the date is older. And sure enough, all of the old data had been fixed. There were no broken records. It's only the new data that had broken records in it. So our fix worked. We just happen to have inserted new bad records. So what do we do about it? Well, we're going to need to make a new view that describes the updates that we want to make. So in this case, let's do select star from updates. Remember, updates is a view. So we had made updates earlier in the previous session. Let's go back and see where we defined the view updates. Create or replace, where is that? Create and replace temporary view updates. And we're going to query the silver table, and we're going to do the average heart rate over a rolling window to populate any records where the heart rate had been reported as negative. So we're going to compute the average heart rate over a rolling window of time for any data point where the heart rate was less than 0. And that's going to be our solution. And what's really cool is because this is a view, I don't even have to regenerate that table. I just query it. And there's my 3 corrections that I want to make. Views are really neat because they stay up to date automatically, because really when I query a view, I'm querying the underlying table with this data or with this query string. So my view is already up to date and ready to tell me how to fix my data. So all I need to do at this point is come up with the code I want to run for my upsert. And in this case, all I want to do is the updates. I don't have any new data I want to insert, so I'll comment out my insert. And now we see that my upsert table has just the 3 rows I want to fix. And so I can rerun this merge. All right, now we'll do a select statement. And sure enough, I have no more broken readings. Yay! That is great news. My sum is empty because there are no more broken readings. So we have fixed our data, and that serves as a nice review of what we had done using upserts previously. So we do our quick verification, and we saw that once we did our query, let's see here where we did the fix, we got null, meaning there were no more broken records. So that finishes our review of what we've covered already. Now we can start doing some additional records here. So this particular version of the course material, instead of doing GDPR, it's using something very similar, California Consumer Protection Privacy Act, CCPA. That's the same idea as GDPR. It's just a law that we have to have that says that users have the right to request that their data be expunged from our database. So whether it's California Consumer Privacy Act or it's the general data protection regulations in the EU, the bottom line is a user is going to come to us and say, I want to delete my data from your database. How do we do that in our data warehouse? So this introduces the opportunity to just introduce some more data modeling language. So in this case, our data manipulation language. So I'm going to drop one of the user's data from our system. So in this case, where the device was 4. So I grab it, and let's actually run this code. I come down here, I want to delete from Health Tracker Silver where the device ID is 4. And now let's just make sure it was successful. Select star from Health Tracker Silver, where P device ID equals 4, and I should get nothing back. Woohoo! It's an empty result set compared to if I do device 3, I get my results. And if I show the history of my table, describe history, Health Tracker Silver, I can see, in fact, that there was a delete operation performed, and I can even see what that delete operation was. I'm doing it where device ID was 4, and I can see who did that delete, which is really cool. So we just did a moment here where we did describe history, and we could see this history where we did our delete. But remember, I have the ability to do time travel series here. So for example, I might want to do select count from version 0 or version 1. I've been showing you how we could go back in time and view previous versions of our table. Let's go back and do that in our notebook. So I look at version 0. I had 3,700 records. By the time I got to version 1, I had added more records, and I'm at 7,100. I get to version 2, I'm going to insert a few more records, and I'm at 72,000. Version 3, I was just doing an optimize, so I was improving the query performance, but I didn't change the data, so it stays at 72,000. With version 4, I'm now fixing broken records, but I'm not adding anything new. So I'm staying at 72,000, but I've improved or corrected the data. And then by the time I get to version 5, I've deleted one of the users, so my count dropped back down again. So this is really good, but it raises a natural concern here. And the natural concern would be, what happens if I go backwards in time and access old copies of the data? We're going to have to do something about that. Before we get there, though, I wanted to point out the transaction log one more time, because I think the transaction log is really important. It's what brings this whole thing together. So I'm viewing the transaction log when I do this describe history, and notice I'm able to really get interesting data about each operation in terms of whether or not I'm doing an insert, whether I'm doing appending more data. Here's an append operation. Here's a case where I did that merge operation. What was I merging on? There was the optimize operation, a merge operation, a delete operation. I can really see what changed in my table. I can also get lots of really useful information about the number of files that were affected in each of these operations. Very useful data and stats in my history. And I'll encourage people to look at those stats if you're doing this online on your own. But for now, I want to take a look at this directory here, the Delta log. And there you see that I'm really dropping a new JSON file for each write that I do. I'm dropping a new JSON file that has the metadata that tells me which files are active and valid and which files are no longer valid. And every 10 JSON files that are written out, it will eventually create a snapshot. So I don't actually have 10 JSON files in here, but when I get to my 10th JSON file, it will create what's known as a checkpoint and roll up all of the data that's been memorized by each of the 10 so that I don't have to read from the beginning of time. It'll create a checkpoint every 10th JSON file to speed up reads. All right, so let's continue on at this point. So before we actually try to deal with GDPR, we're on our way towards dealing with GDPR. What if I accidentally deleted data that I didn't mean to delete? So in this case, we deleted all the records for device 4. But let's say that the user didn't actually want us to delete all their devices data. They just wanted their name removed. Oh shoot, we did a delete we didn't mean to do. What can we do about that? Well, we're going to need to do another merge operation. In this case, we're going to need to do an upsert, but this time recovering any broken data, and we're going to just replace the name column with null in the process. So what I could do is make a new view that describes the data that I want to be updating. So I'll create a new view that describes the data that I want to be updating here. So upserts, that's always the new data I want to insert. You can call it any name you want. It doesn't have to be called upsert. And I'm going to select null for the name, but I'm going to keep the heart rate. And I'm going to go back to a previous version of my table. Let's see which previous version I want. I want to go back to version 4 before I had done this delete operation. So I'll go back to version 4, and I'm going to grab it just for that user that I had deleted the data for, device number 4. So I'm going to scrub the name, but restore the rest of the record. So I can go back in time, grab the old data. So let's see what it's going to look like now. Select star from upserts, and we're going to add this back into our database because I'm able to do this data recovery. So we're going to scrub their name, but keep their heart rate. So it's no longer personally identifiable information, but it's still useful for science purposes. So now we just need to do our merge operation. So just like we did before, we're just going to copy the exact same merge command that we used earlier. If it is in there, do an update. If it's not in there, do an insert. In this case, none of them are in there, so it's going to be doing an insert for everything. And now let's do a count to see that we were successful. So select count star from Health Tracker Silver, and I'm back up to 72,000 records. But if I ask for device 4, and let's just limit it to 10 rows, notice that the name is null. And if I get it for device 3, I still have my user's name in here. Now, quick privacy protection. This is not a real person. All the data you see here is synthetic, fake data. Very important when we're dealing with any kind of healthcare. So we used a Python package that generates fake names. This is one of the fake names that it generated. And similarly, fake heart rates and things of that nature. All right. So we just did a count and we saw that we are up to 72,000 records, which is really important. So let's go back now and view the history. And my history here is not going to match what you see in the courseware because remember, I did that optimize command. So mine's going to be version 6 as opposed to version 5. There we go. My version 6 is that merge. And we could see the change, and we can go in here and we can see, for example, we've got 50 files and we inserted 144 rows and we updated 0 rows. And it was a lot of files, which suggests that there might be value in doing another optimize. So let's go ahead and optimize. Well, actually, yeah, let's do it. Optimize Health Tracker Silver. And that's going to reduce the number of files that I have to query again. Now, again, don't optimize until you're done with all of your updates. So optimize is something that you do when you're done making your updates for the day, and you want to just make sure that queries are fast. You're not going to optimize between each and every operation, but just when you're done for the day. And notice it didn't take as long to optimize today as it did yesterday, because it only needed to optimize newly written records. It didn't need to optimize files that had been previously optimized, which is really nice. So it's removed 54 files, which is really nice. Now the files are still there on disk, they've been marked inactive. And if I wanted to, I could Z-order by, let's just Z-order by name. I don't want to Z-order by device ID because I'm partitioning by device ID, so that would be redundant. So I'll Z-order by name just to show you the Z-order. And that's going to say people with the same name should be in the same file. Okay. Notice now we've got null and all the records. We did that as part of our coding. So this is good, except for the fact that the user's data has not been truly expunged from the system. And the reason we can say that is let's go back and run this query for device 4. We see that his name was expunged, but if I do version as of version 3, where's my typo? I must have a typo in here and I'm just not spotting it. Oh, this version as of goes on the table name. Version as of 3, because I'm doing the table version as of 3. There we go. Limit 10. If I go back in time, I can still see this guy's name. So I haven't actually honored the GDPR requirement that I expunge him from my system. That's problematic. So I need to actually get rid of him from the historical copy of the table as well. So how do I do that? Well, this is where vacuum is going to come in. So what I'd like to do would be to say vacuum, don't keep the latest 0 hours. So I'm going to say get rid of everything that's old, retain nothing. But when I run this, Spark is going to give me a warning. It says, are you sure you would like to vacuum files with such a low retention period? If you have people that are currently reading or writing to the table, it's possible that you're going to break their job because the old copy of the data will be gone. You're going to break jobs that are running today. Now, if they were just reading, you're going to break the read operation, but it'd be even more serious if they were in the middle of writing. If they were in the middle of writing and I delete the files from underneath them, I could break their write job, which would be very, very bad. So what I want to do is only delete for such a short retention period. Remember, the default warning is for a week, but I can turn off that warning. So I could go set retention check enabled false, and that's going to say I'm going to let you vacuum less than 1 week. I'm going to allow you to have retention periods that are less than 1 week. I really do mean to do this. And now I can vacuum and get rid of all the old files. So I vacuumed that directory. Let's take a look at the directory at this point. %fs ls. Notice I still have my partitions. I have to have a minimum of 1 file per partition. But within a partition, I'm down to having a single file. I've gotten rid of all of the old files. So now if I try to time travel, so I'll come back up here where I asked for version 3. I get an error message. Read file exception. Error reading this file part. The file reference cannot be found. This occurs when the data has been manually deleted. So in this case, it occurred because of my vacuum command. And then there's a little link to a doc with some frequently asked questions to describe how to handle that exception. So time travel has been made unavailable because I removed the old versions, but this gives me the ability to make certain that data that I wanted to redact from my system is gone. So we're using GDPR as an excuse to demonstrate the vacuum feature, where I clean up old versions of the data. So at this point, we attempted to query and we got the error message. So I'm going to look now to see what kinds of questions I can find. Oh, there's some good ones, but I'm going to come back and answer those in just a moment, I think. I'll do this summary bit right here, and then we're going to lead into the streaming component of this discussion. So for the moment here, let's just do a quick review. So we did the following steps. We read data from our operational systems. So they got dumped into some kind of bronze storage. That is, we're capturing all of the data from my various operational data stores. And we then read that into Databricks as our bronze table. We then cleaned it to be our silver table. And then we're able to make our gold table that represents the data marts. But what we haven't done is kept our gold tables up to date with the latest modifications to the silver table. So that's where streaming is going to come in, and it's going to be our next stop. So we've converted a Parquet file to Delta Lake. We've done batch updates of data. We've identified broken data. We've done upserts to fix broken data. We've time travel to go back and look at older data, and then we've scrubbed personal data from our user. And this is a nice little narrative demonstrating the power of using a data lake to do the types of workloads that used to only be available and only be possible in a data warehouse software system. Now I'm using a data lake to do it, which gives me all of the scalability and benefits of a data lake with the capabilities of a data warehouse. Merging those two ideas, which is this vision statement of the lakehouse. So now I'm going to go and answer some questions that have popped up, and then we're going to dive into streaming. So one question is from Martin. Martin had said, are views always temporary? So let's go to an example of a view that doesn't necessarily need to be temporary. So we had a view here called broken records, broken readings. And right now I should have 0 broken readings. Let's find out. Yep, no more broken readings because we fixed everything. But this is a really useful view. Now, if I make it a temporary view, then this view is visible only within the scope of this notebook. It's only visible within this notebook. So it's really nice when I want to just do something temporarily as part of a job, and I don't want it to be permanent and to stick around. If I want the view to be visible across notebooks, but within an individual cluster, I can even make it a global temporary view, and it'd be visible to other notebooks, but only if we're running on the same cluster. But I'm also able to make a permanent view. So let's get rid of the old view. And it's a little bit annoying in the DDL. If it's a temporary view, I still say drop table. But if it was a non-temporary view, I'd have to say drop view. It's this idiosyncrasy in the SQL language here that we're using. But I can create a permanent view as well. I can create permanent views only if it's a permanent table that I'm querying. So in this case, I'm only querying an actual table. So I can make a view of a table. And by permanent, that means this view is going to remain defined even after I restart the cluster. And it's visible from other clusters as well. But it's still a just-in-time query. When I query the view, I'm really querying this table. But now it's going to persist across restarts, which is really nice. So that should answer your question, Martin. Could you make a permanent view? And the answer is yes, as long as you're only querying tables. And it registers the view as a view in the Hive metastore. Let's see here. There's some other questions that people have asked. Seren asked, can you collect statistics to help with data skipping? So that was the idea that we talked about, where when you, for example, Z-order, you can put files that have related data together. And if I do describe history here, you saw that I did that optimize command where I Z-ordered things and put related data together. However, what's missing from that is understanding how under the hood, it's able to figure out which files to read. And that's not something that's visible here but it is visible if I was to read the actual JSON file. So let me see here. If I go describe extended, health tracker silver, and I look at the metadata, so let's go down and look at version 7. And let's just look at the contents of that JSON file. So it's not the prettiest reading this JSON file here, but it will tell you, let's see, it says I removed all these 50 old files. Notice they got removed. And then it tells me that I wrote this new file right here. And it's keeping some statistics around, like it is partition 4 for the device ID, and the minimum record for heart rate is 39.2, and the maximum value for heart rate is 185. And we can look at other things as well, like what was the minimum and maximum value for the dates column. And what this allows us to do is that if I do a query and I ask for heart rates of less than 39 beats per minute, that would be an incredibly low heart rate. But if I ask for heart rate beats of less than that, Spark is smart enough to not even query that file, which is really nice. So it keeps some minimum and maximum values around in order to prune which files it reads for efficiency purposes. So if I had Z-ordered by name, it would be able to use this to figure out which files, what's the minimum and maximum name, and would determine which files have people with that name, and I'll only query those files using these statistics. I'm actually able to compute even more detailed statistics if I wanted to. I could go analyze table health tracker silver, compute statistics for column name, or better yet, column heart rate, and I'll analyze table, compute the compute statistics for column heart rate, or for columns. I go to list the columns. All right. There we go. And it actually creates even more detailed statistics to help me skip files. And so computing statistics can be really useful to speed up queries because it's able to prune which files it reads. So this is the type of thing that we would cover how to do in our performance tuning courses. And you can go to academy.databricks.com. We have performance tuning courses that we run once a month, and you can participate them online. But this is the type of thing that we would teach in those courses, and that helps speed up the ability to do query optimization and to drop file parts that we don't need. It also helps with optimizing joins. We can do things like broadcast joins. Somebody asked, can we demonstrate some of the autoloaders? I'm not going to, so there are some really great integrations, by the way, that we have to help load data and ingest data into Databricks. That's beyond the scope of what we're going to be covering in this webinar, those autoloaders, but you're welcome to reach out to our team, a sales team, and say, hey, I'd really like to see this feature of Databricks, and our sales team can set up a demo for you. So feel free to reach out. When we go back to that Q&A slide that I have here, you can reach out to one of our Spark experts, and they can demonstrate some of those features that they would be useful to you. And one of the things we have definitely seen is that Delta Lakes, because it's running on Spark, is significantly faster to a traditional Hadoop Hive implementation. It is significantly faster and often a lot cheaper as well because they get to run on a smaller cluster size. And our sales team can provide you performance comparisons with things like HBase and Oracle as well. I would rather leave those comparisons though to the experts. So I'm going to encourage you to reach out to sales. Let's see, what other questions do we have here? What mechanisms exist today to mask out PII data in and out of the platform? So Santosh, we just demonstrated how you can actually, with your queries, really filter out the PIIs. You can update the data. Another thing you can actually do is you can create a view that masks data from an underlying table so that the table still has it, but the view is hiding it from you. And Databricks is in the process right now of getting high trust certification, which is one of the gold certifications for the healthcare industry when it comes to being able to deal with private data. So you can talk to our sales team. We are SOC 2 compliant and a number of other things to really make sure that your PII, personally identifiable information, PII's personally identifiable information, is protected in some way. Durgadas just asked, what is the checksum file that he saw in there? So that's just to make sure that the JSON file was written and wasn't scrambled. So Spark verifies the checksum so that if the JSON file has been manipulated in any way, Spark detects that and marks that version invalid. It's like the transaction failed. It's just a safety feature to make sure that data doesn't get corrupted. All right, let me see if there are any other ones, and then I want to move on to streaming here. Alessandra asked, what about for auditing for regulation's sake? So there's a couple of options for auditing, Alessandro. One of the ones that you saw is that I can just view the version history of a Delta table, which is incredibly powerful. Being able to view the version history of what changed in the table. Where was an example of where I did that? It was right down here. View the version history, who changed what? And being able to go back and access previous versions of the data is incredibly powerful for auditing needs. The other thing that you can actually do is, if necessary, there are features that you can work with Databricks to turn on where you can audit who ran what commands in Databricks and view the entire history of jobs that have been run. So it's possible to log, for audit purposes inside of the Databricks platform, every command that every user has run. That's something you have to work with us and ask us to turn on. All right, let's go ahead now and keep going towards streaming. So at this point, we're going to go back to this workshop. And you notice there's this new course that's been added here, Demonstration Notebooks, How to Build a Cloud Data Platform for BI and ML. And this has new content that we have made available. So I'm going to click on this third course. And rather than working from inside of slides, this one is going to be in the format of notebooks that you download. And notice it ends in a DBC. So I'm going to click on this download here where it says material, download. What I'm downloading, notice it comes down as a DBC file. So what that means is that I need to log into Databricks. You can log into Databricks Community Edition or a regular version of Databricks. Click on Home. I'm going to click on this little drop down and select Import. And I import these notebooks directly into Databricks. And what you're going to see is there's the Spark demo from our first webinars in here, as well as a demo that I'll briefly touch on that just revisits a little bit about Delta. And then we are going to look, this is the one we're going to do today, 02 Delta architecture that deals with streaming. This is the notebook we're going to use today. And then there's other content on machine learning and ML flow and some other really powerful demos. These will be some source material for next session tomorrow, where we look at doing machine learning and business intelligence on Databricks. I'm going to be looking at notebook number 2 right now. Now, if you missed those instructions as I did them, let me go back to the website. Notice there's a link. When you've successfully downloaded the notebook, follow these instructions to import it into your Databricks workspace. And that will take you to a web page that will walk you step by step how to import notebooks into your Databricks workspace. And once they're imported, we can open up that notebook, and this is going to form the basis for this next lesson. And I would encourage you right now to just watch, either pause if you're watching the recording and import it, or if you're watching live, just watch me and then worry about importing the notebooks afterwards. So here, we're going to talk about how Delta can keep our tables up to date and how this eliminates the need for the traditional Lambda architecture. So what exactly is Lambda architecture? Well, Lambda architecture is this idea that I've got data coming in, and I want to populate a data warehouse with it. So I'm going to use Spark to save the data to my data warehouse. And then I have batch jobs that clean up that data and make tables that I can query. And I'm able to do batch queries and do reporting on them. But the problem is these batch jobs may run once a night. And I want to be able to do reports that not only look at the historical data, but take into account some of the latest changes. And so people first have this data warehouse that they build that allows me to query historical data, and they want to have dashboards that are showing the latest data. So they do a batch job version, and then they repeat the logic using streaming so they can get live up to the minute data. But notice this fork in the road. It creates this picture that looks like the Greek letter lambda. And basically, I'm doing it once as batch and again as streaming, all because I want to be able to keep a copy of the data around in my data warehouse, but I also want live up to the minute views of the data. And Lambda architecture was really successful from the standpoint of making it even possible to do this, but it's really tedious because I am writing the data both to my data warehouse and again, rewriting the data using a streaming platform like Kafka. And that is a lot of redundant work. So what we're going to do in Databricks with Delta is it enables us an alternative to this Lambda architecture. It enables an alternative to the Lambda architecture where we're going to have, again, that bronze, silver, gold modality where my bronze tables are the ingest, and I can have many different sources of data coming into those bronze tables. They can be live streaming data from Kafka or static data coming from JSON files, CSV files, and other things, but constantly being made available and being ingested into my bronze table. But what's really cool is that my bronze table can then be the data source for a streaming job that keeps my silver tables up to date. So I'm not just streaming into my bronze tables anymore. I'm going to stream out of the bronze tables and into my silver tables and do my data cleansing. And then I'll have a streaming job that'll go from my silver tables into my gold tables so that I can get up to the minute reporting with my analytics. And as new data arrives, I get to write it out to my data warehouse and keep my downstream tables continuously updating as if they were materialized views. They're continuously updating. Whenever the bronze table changes, these chain tables will pick up those changes on a continuous basis and allow me to report the changes. Now, I use the term continuous basis loosely because I get to set the policies about how frequently it pushes these trickle-down changes. I can have it be doing this every few seconds, or I can actually set it to run this update once a day. It doesn't matter. I'm still going to use the streaming architecture to do it so that I only deal with newly added records. And I get all of the benefits that come with having these transactional guarantees. Now, how is it possible that I'm able to ask what's new in my bronze table or what's new in my silver table? And the answer is that transaction log, that delta log. It tells me which files have been deleted and which files have been added. So I'm immediately able to determine what's been taken out and what's been added. And I'm able to quickly identify new records in my system. And by identifying new records, by looking at those transaction logs, I'm able to say, give me what's new so I can update the contents of a downstream table. Jason just asked the question, could I not go back in time? Oh, I think that was an earlier question, my bad. He said, where I violate the user data protection by going back in time. The answer to that was, yes, that's what vacuum was for, was to make sure that we could get rid of the data with the time travel, get rid of the previous versions of the table. My bad, I thought when I first paused, I thought it was a question related to Delta here. So here we go. Create Leader asked, how do we resolve this by using the Delta architecture? And the answer is, I'm able to use a table as a streaming source. So let's go through an example of actually doing that. We're going to use this Delta architecture so that I can keep my data up to date. I don't have to keep it updated daily, but I can instead have it updated every few hours or even every few minutes. Again, I don't have the duplicate data or duplicate code that was required for Lambda architectures. And I have the full power of Delta to be able to do things like change data capture, GDPR, sessionization, deduplication. All of these typically hard problems are a lot easier to tackle with Delta. And now I can keep these tables up to date by combining it with structured streaming. And we have seen organizations reduce their costs tremendously. There is a terrific presentation I want to point people to who are interested in getting some historical presentations on case studies on how this Delta architecture has really improved. There is this fantastic talk, a keynote that was delivered at one of the Spark summits. And I put it in here in notebook 00. But you get one of the largest companies in the world who talk about how they were able to use Delta lakes to reduce the time at which it took to build a system that was gathering events from an Internet of Things via streaming, real-time security events, and populate these tables that allowed them to do security event detection. And they were able to stand this whole thing up with 3 engineers in just a couple of weeks. I don't remember the exact number of weeks. I think it was like 4 or 8 weeks. But just 3 engineers were able to do this with a huge amount of data. And it was so much simpler than what they were trying to do before using the Lambda architecture. So I would highly encourage people to go and watch this video. It's available, it's public, and it really talks about the use of Delta to solve this type of problem. Now, continuing on talking about Delta and the Delta architecture, let's go ahead and do a demonstration notebook. So first, I'm going to create a database if it doesn't exist. So we already have our DB Academy database, so that's kind of a no-op at this point because it does exist, but I'm going to make sure I use that database. If I click over here on data, remember I see DB Academy is listed here now, and that's where my tables are put. And this allows me to keep my tables separate from other people's tables. And then in a lot of example notebooks, you'll see a line of code that looks like this, where you're setting the number of shuffle partitions. So whenever Spark is reading a table that might be broken up into multiple files, and let's say it's doing a sort, so it needs to move data around. It's what's called a shuffle. It's got, maybe A's in this record, but I also have some A's down here, and it needs to get all the A's together as part of sorting. It needs to reorganize the data, and this is known as shuffling. And it makes new files, and let's say it moves all the A's up here into this file so that I can sort the data or get rid of duplicates if I'm doing a distinct operation. Well, the challenge is it needs to know how many files to make, and that's really hard for Spark to know up front how many files there should be. So the default in Spark is to make 200 files. So it literally makes 200 files every time. And the reason that's the default is that it works well for 95% of the data sets out there. If your data is pathologically huge, you would need more than 200 files. If your data was really small, you could get away with fewer than 200 files. But 200 is this great default because it works for most jobs. And so we usually tell people just go with the default. If your data is small, sure, you could go with smaller number of files, but it's small. It's going to run fast no matter what. You really want to optimize for the case where the data is big, and you leave it at 200. Now, in our example, our data is pretty small because I wanted it to run fast. I didn't want to wait, 3 or 4 minutes for it to finish computing. So our data is small. So I could shrink the number 200 down to the actual number of CPU cores in my cluster. So if I want to find out how many CPU cores in my cluster, I actually have a pretty big cluster running right now with 64 cores because I wanted my jobs to run really fast so that you wouldn't have real-time pauses. But if you were running on Databricks Community Edition, you would only have 2 cores. And so for small data, setting the number of shuffle partitions to match the number of CPUs means the number of files that I create match the number of CPUs, and I get full usage of my cluster. So I could downsize if I wanted to for small data. And I want to emphasize downsizing is something you do for small data, not for your typical jobs. So you're going to see this type of code in a lot of our notebooks where we downsize it to match the number of CPUs in our cluster. Now, let's start working with the data lake here. So with streaming data. So first of all, where are we going to get our streaming data from? Well, this is the source of our streaming data. Notice it's just an S3 bucket. But what I'm going to do is control copying of data from here into a drop directory for as if new files were arriving. So this is where we're really going to put the streaming data, is into this folder. And when new data arrives in this folder, I'm going to pick it up for processing. And I'll write it into my bronze directory. And then eventually I'll create cleaned data sets for my silver tables. And then I'll do my reports and aggregations and make a gold table. And for all of this, we're going to do streaming. Now, while we do streaming jobs require that we keep a file that tells you the state of the current streaming job so that if for any reason the cluster loses power or restarts, I can pick up from where I left off. So in structured streaming, it's going to write where we are so that whenever it goes to do the next job, if there was a power outage or my cluster had shut down, I can recover. So that's these checkpointing directories. So I'm just setting up some constants here. Where am I going to put my bronze table? Where am I going to put my silver table? Where am I going to put my gold table? Where's my data going to be that I'm reading from when I'm doing streaming? And where are these checkpoints going to be? And here's a little command. It's just going to delete any past runs of my notebook here. And oops, I forgot to run this base path. So there we go. My constants are defined, and now I can delete any files that might have been lingering around from previous runs of this notebook. All right, so everything you'll notice that I write is in this directory. If you are on a shared cluster with other people, I would recommend you put your name in this so that you're not clobbered with other people if you're both running this demo at the same time. And now we're going to work with our example that we've been doing where we have a health tracker. So in this example, our health tracker, we've got a device. Oops. We have the time that it got a recording and what was your heart rate. But for the interest of making our example, or for the purposes of making our example interesting, we're going to have a medical record number associated with the device, and I'm going to have to join it against another table that has my personally identifiable information, like my name. I'm going to have to join that against another table, and this is a way of helping to protect people's identity a little bit. I'm keeping the actual username of a device in some other table, and PII stands for personally identifiable information. It's relevant in privacy regulations. Technically, a medical record number is still considered personally identifiable information if it could be used in any form at any time to eventually get to a person's name, according to those rules. But I've split this up into 2 tables, and streaming in are going to be these recordings of your fitness device. My wife actually currently works at Fitbit, so she helped inspire this example. Now, I've got a little program that we're going to write that's just going to simulate files arriving. So this is the little helper class, and it's going to copy data from S3 into that streaming directory. So to demonstrate that, I'm going to just go new file.arrival. And what you're going to see is an error message telling me that I'm not allowed to read from Amazon S3. Grr. There is no problem. I've got a temporary fix right now, but if you actually had gone to lesson 1 and run this classroom setup from lesson 1, it will make available an alternate way for us to access this S3 directory, which would be under DBFS mount training healthcare. So I had tried to be a little too clever and went to the S3 bucket directly, but now it's complaining it wants the access keys. And I'm going to instead just access it via DBFS. Remember, you have to run that classroom setup from 0-1 to make that work. You're welcome, of course, to put in your own AWS keys if you wanted to read from that AWS path, because it is a public directory. All right, so now let's come in and run this example. Oops, I need to run. Nope, there we go. This is. All right, I don't have 2 slashes in DBFS, just 1 slash. Last try. Now you know this is live, it's not a recording, at least for those of you who are watching it live. It will eventually be turned into a recording. All right, and so notice that it dropped a file off in this directory. And then if I run it again, new file.arrival, it acts like another file has been dropped off in our directory. So it's my way of simulating streaming because I haven't set up an actual Kafka server. I'm just going to simulate streaming by dropping new files off in a directory. And that is one of the modalities that is perfectly available for anybody who's doing a streaming job. So we come down here now, I'm going to go spark.readstream, and I'm just going to read files from this directory here. Now, in this case, for my bronze, I'm not even going to bother parsing the JSON initially for my bronze tables. I just want to capture that data. So I'm just going to read it in as a text file. So it's going to be 1 string per line. So I go spark.readstream, text file. I give it my schema. Since I want to simulate live streaming data, I'm going to tell it only read 1 JSON file for every batch job, or every time it does a streaming operation, read 1 file at a time. Generally in production, you'd say if there are 50 files that just showed up in your directory, read all 50. So that I can make the feel of streaming, I'm telling it to read only 1 at a time, but you wouldn't set that flag in production. And then I give it the directory. And now I'm going to move us into SQL land. So notice that I had to do this in either Python or Scala. So this particular cell is written in Python. If you notice, Python is the default language for my notebook. If it wasn't the default language, I could still specify it's Python by putting Python at the top of my cell. And I'm going to make that data available as a view. Now, this is a streaming view. So what that means is I could turn around and go select count star from recordings raw temp. Oops, and I got to tell it this is a SQL cell because the default language of my notebook is now Python. I need to specify if it's some language other than Python. There you go. 592 records have been read in. And if new data arrived, let's simulate new data arriving here. I'll run the data arrival. Let's watch. Up, it already went up. That was fast. 14,206 records. So it's a streaming query on that data. Now, what I really want to do is to add a little bit more information to my bronze table. I don't just want the JSON file. I want to add when did I grab the JSON file. So I'm going to add a timestamp. And I want to add maybe a label, like where did the data came from? Oh, this data is healthcare recordings. So I'm going to create a temporary view for that. So just to take a look at how it looks now. When it was raw SQL, excuse me, when I was reading from the raw table, select star from raw, notice it was just go back here. When I was reading from the raw table, do it again. Notice I just have the data as a big JSON string. But what I'm adding to it now with this temporary view is just a timestamp and a label. Here's when I got it, and here's the label. And I'm going to dump this into my bronze table. So my bronze table is going to have the raw unparsed JSON and a little bit of meta information in it. I'm not even going to parse the JSON from my bronze table. And the reason for that is that if I parse the JSON, I'm giving it a schema at that point, and I want it to be really, really flexible. Now, there is a bit of a plug for Spark 3.0. Spark 3.0 is actually going to add a JSON data type to be part of Spark so that I can work with JSON natively in my SQL queries. And that'll be really cool. And we're looking forward to the release of Spark 3.0. All right, so with that in mind, we're ready to write the data. We're ready to really kick off the streaming job. So far, I've just been displaying it on my screen. But what I really want to do is to write this out to disk. So I'm going to go and grab the table that we had before, and I'm going to say I'm going to write this out as a Delta file, and I give it a path to where I want to put it. And then remember, the checkpoint is if the streaming job is terminated for any reason, I can resume the streaming job from where it was left off. So here we go. I'm going to read the data from recording bronze temp. I'm going to write it out as a Delta file, appending to any existing data. And I'm going to put it to that path. That's that constant we set up above, bronze path. So now it's writing out, and I can actually create a little streaming job to watch it populate that bronze table live. So I've got a little job here that's going to just give me the count. I can even expand this. I can see how many records it's processing, etc. But I think this is interesting. Okay, we're up at 14,000 in my bronze table currently. And now if a new file arrives, whoa, look at that. It's already moved 33,000 records in there. So the streaming job picked up newly arrived files and immediately put it into my bronze table, which is really cool. But that's just my bronze table. What about my silver table? I'd really like to look at my silver table. So I'm going to leave the streaming job that's reading things into my bronze table. I'm going to leave this available, up and running. Oh, look at that. It's already gone up again. 5,000 or 52,000 records as it's processing. I'm going to stop this. Actually, I can even leave this count running. There's no harm in leaving the count running. I've got a big enough cluster to be able to do that. We'll be able to see these counts increase as new records arrive. So I'm going to leave these streaming jobs up and running, but let's start talking about our silver table now. So let's go back to the picture at the top. We're reading data and dropping it off into our bronze tables. Now I want to read from the bronze table and write it off into my silver tables for query purposes. So this is where parsing the JSON is going to be very important. I want to parse the JSON to make it easy to query, and I want to clean my data. The whole goal of silver tables is ease of querying and cleanliness of data, whereas the whole goal of bronze was just capture it like you got it. Don't change anything in bronze. We do the cleaning at silver. So scroll down again to where we were working with our silver tables. So here we go, silver table. So this time I'm going to go spark.readStream. We're going to read from a Delta file where my bronze table was. And we're just going to make this a temporary view so that I can go back to using SQL. Now, I don't have to make temporary views. I can actually write my queries completely in Python. I could go, for example, select, and then I could start calling, or select expression, and I could start calling functions right in here. And I could start really writing a powerful query. I'd have to worry about quotes inside of quotes. That would be something I would deal with. But the nice thing here is I'm going to go ahead and make this into a temporary view because we've been using SQL all along. Why stop here? The only reason I'm not using SQL for the streaming is that there's not a streaming API for SQL. So I had to use Python to describe the streaming portion, but I'm going to use SQL for all of the data transformations. So the first step will be to read as a stream the bronze table and make it available as a view. And now remember, I can query that view. Select star from bronze unparsed temp, %SQL. So I can query that table, and this is going to be kept up to date as new data arrives. If I had done a count star, you would actually see that count updating. It's showing me what that table looked like in real time. It's a view of streaming data at this point. Now I'm just going to run my SQL. I should have stopped the job before I deleted the cell. Oh well. I'm going to run, and I'm going to create a new temporary view that is going to parse the JSON data. So I give it the JSON data and a schema, and it's going to parse the JSON data using the provided schema. And it's going to make that available as a temporary view. And then I'm going to write that temporary view back out to disk as a silver table. So recordings parsed path is going to be where I'm going to put my silver table. We're going to write it back out to disk, and let's watch the count increase. I've got to do this again. I have to wait for it to write to the directory before I can start reading from the directory. I had a small race condition there. Needed it to start writing before I can read. But now we can watch the count increase over time as the streaming job is busy catching up. It's reading what's in the bronze table. And now my silver table has 52,000 records. Now at this point, I am going to simulate a new file arriving. So the file is going to arrive and go into my bronze table. And then my bronze table is going to update my silver table. So let's trigger a new file arrival and see the bronze job start running. And then once it's in the bronze table, the silver streaming job will run and put it into the silver table. So let's scroll up. First we see here's the bronze job just started running. And then we're going to see this count increase. Let's wait for the count to increase. There it is. The count just went up. Now let's come down here to the silver. Oh, the silver was real. No. Further down. Where was my silver table? Up here. Okay. And yep, my count went up for the silver table as well. I was hoping to scroll fast enough that we could watch the count go live, but that silver job ran right then and increased its count. So I now have new data. So you see that as new data arrived in the bronze table, this streaming job is reading from the bronze table and keeping the silver table up to date. Now let's imagine for a second that my job dies. And now new data arrives in my bronze table. So let's wait for new data to arrive in my bronze table up here. The bronze job is now running. Let's see this count go up as soon as it's done. There it is, 73,000. Notice that my silver table is still at 63,000 because I killed the streaming job that was reading from the bronze table and writing to the silver table. And it's not at all unusual that you might have a cluster failure or something of that nature. Well, that's the purpose of this checkpoint directory. Let's take a quick look at the checkpoint directory. If I want to use a constant, I got to write it in Python. This is a Python variable. Let's take a look at that directory using Python here. And I can see the commits and the offsets of how much it's read so far. So this is basically just keeping a record of how much data has it read up till this point. And let me see here. If I do a head, I should even be able to see the contents of that file. Let's see. There it is, the little JSON file, and it tells me I have read up to this state of the file. Here we go. Where is it? Reservoir version, source version 1. It's tracking the versions of my bronze table that it has read so far. So that when I restart the job, it's going to pick up where it left off and only run what's new since it last populated the silver table. So let's watch. It's now populating the silver table, and we should very soon see our count go up. So it's restarting the job from the checkpoint, and it's going to update the silver table, and there it is. Our count has finally gone up to match what's been added to the bronze table. So we get some fault tolerance using that checkpoint directory. So this is cool. I now have a silver table, but I'd like to be able to join data from that silver table to a static lookup table to further enrich my data. So in this case, I'm going to read a CSV file and make that available as a temporary view. Now I could mount the CSV file using SQL, but this one happens to be done in Python. I could just as easily go %SQL, create temporary view PII using CSV, location, and give it the path. And I would actually get to see it. This is doing the exact same thing. It's saying read a CSV file. Here's the schema. The first line is a header. Grab it from this directory and make it a temporary view. Options, infer, schema equals true, and header equals true. And then I'd have to actually get this path. So let's grab this path. Okay, oh, fine. To put the path as an option. So I could be creating this using SQL, or I could create this using Python. So if I run the Python, notice it says create or replace temporary view. So it's going to create or replace temporary view and make it available. They do the exact same thing. So the point is, at this point, I can now query that table with my personally identifiable information and map the medical record number to a real name. And again, this personally identifiable information are fake people so that we're not exposing anybody's real health information. So now what I want to do is I want to read from my silver table, and I'm going to join the silver table with that PII table. And as well, I'm going to only keep ones where the data is clean. That is, heart rate is greater than 0. I'll even cast the timestamps to be a true timestamp type, because right now it is being represented as a string. So I'm doing further data cleansing to really make useful silver tables. So, oops, first I need to read the recordings. Now I can join them together and write that back out as another silver level table that has further enrichment. In fact, I may choose to only have ever written this out and not even keep that other silver table. I could do my architecture as one silver feeding into another silver table, or I can do my architecture where I only keep the final silver tables. But here, I'm just populating a new silver table. Let's take a look at the count of my new table. So make sure that all the data got in there. So now I'm going from raw files to bronze, from bronze to my first silver, from my first silver to a second silver that enriched the data and did further cleansing. And eventually I'm going to want to create my gold table that has the report. So it's this pipeline of updates to my data. So now when a new file arrives, it's going to take a little bit longer because first the bronze table will have to update, then the silver tables will have to update. So let's give this maybe 30 seconds and see that count go up. There it is, 96,000. So my entire data warehouse is incrementally updating as new data arrives. And so we can finally bring this home by doing our gold table. So I'm going to read from my silver table. And this time I'm going to collect averages. So I'm going to group by medical record number and name and date, but only by day. So I'm going to group by day. And I'm going to look at each user's average heart rate for an entire day. And that's going to be my aggregate reporting that I want to be monitoring and make available to my data scientists. So I can create a temporary view on this. I could even make this a permanent view because I'm actually reading from, well, actually, no, I can't make this a permanent view because I'm reading from a temporary view up here. That's my streaming data. So I'll make it a temporary view. But I really want it to be available all the time. So what I'm going to do is I'm going to write this temporary view out. By the way, I'm going to just show you querying the temporary view. Select star from patient average, %SQL. So it is doing those averagings when I query that temporary view. And that is really nice, but notice it's taking some time to compute those averages. And this is the benefit of adding a gold table, is that instead of querying the silver tables directly, I can save these averages out to a gold table for faster responsiveness. So now I can see Michelle Carter's average heart rate for the day was 85 beats per minute. I think I said beats per second earlier. That would be a very high heart rate, 85 beats per minute. So how do we save this off to a table that is just continuously updated and therefore faster to query? Well, again, we're going to go Spark dot, we're going to read our temporary view, we're going to write it out to a gold table. Because we're doing aggregations, we're not just appending anymore. Aggregations are subject to change. So we're going to say every batch interval, write out a fresh, complete copy of the gold table. So write out everything. You could also do update, which says only write out what's changed, but that only works if the underlying data store is like a relational database that can update individual rows. Since we're using Delta, we're going to say write the whole file. And let's run this, and then I'll talk about the trigger once in just a moment. So I run this, and instead of being a streaming job that's displaying it to screen, it's going to write it out to disk. And then I could turn around and say, create a table pointing to that location on disk. And at that point, I can query that table. And notice that querying the table is significantly faster than if it was a streaming job. And here we go. I can look at people's heart rates by date and by person. And I can see this guy's average heart rate for that day was really, really high. There's obviously a health information going on, or a health concern going on here. Other people took off their fitness monitors on certain dates. And I can see that as well very quickly from my plot. And in this case, the reason it came up plotted is because while I was preparing the webinar, I had already set these plot options. So I said it's a line chart grouped by name. The x-axis will be the date and the y-axis will be the average heart rate. And it remembered that and it displayed it as a plot. The first time I ran it, it actually showed it as a table. And then I had to click this button to turn it into a plot. Oops. And apparently I've just somehow clobbered my plot options. Let's go back. Date, name, average heart rate. Oh, it's because it's a bar chart and I wanted it to be a line chart. There we go. And it looks a little bit prettier. All right, so now what is this flag we put in here where we say trigger once? And this is because there's this question that you guys have been asking in Slack here, or not Slack, but in our Q&A forum. They said, is it necessary to leave my streaming job running all the time? If you notice up here, these streaming jobs are still running and ingesting new data. Is it necessary I leave a cluster up all the time so that my data can be updated? And I already showed you it is allowed, you're allowed to stop a job and restart it. So what if I wanted to just run one streaming job just once and then have it stop? So it reads the data, updates my table. Where was I? Reads the data, updates my table, and then stops the streaming job. And then what I could do is I could set a nightly process to run the streaming job once an hour or once a night and shut down the servers in the meantime. So by stopping, I allow the server to then shut down. And then I can come over here to the Jobs tab in Databricks, create a demo streaming job, and I say, I'd like you to run my webinar, Delta Architecture, and I'd like you to run it on a schedule of once a day. And I would like you to launch a brand new cluster just while that job is running. So this job will run on a fresh cluster that nobody else is using. I can choose how big a machine to give it, how many executors to give it. I can even attach libraries to it. There's an option here to attach libraries. And now it will run that job once a day. It'll run that notebook. So if let's go back to my notebook. If all of the cells in my notebook were written with trigger once, so if all of them had trigger once equals true, then instead of running continuously, they would simply process what's new and then shut down so that I'm not paying for the cluster except when I'm doing an update. I get all the benefits of streaming in the sense that I'm only going to process what's new. I don't have to do all the work. I'm only processing what's new, but I don't have to leave the cluster up and running. So this is an incredibly powerful pattern. I'm going to go to all of my previous cells at this point where I had a write operation. So I'm going to search for the word .write. And I'm going to tell it trigger once. Everywhere that I was doing a write operation, trigger once. Everywhere that I had a write operation, trigger once. All right, and then the other thing I have to look for is where I was displaying code. So here I was displaying the count. Technically, I would need to say trigger once in here as well. I'm just going to comment out the display because I'm running it as a nightly batch job. There's no point anymore of displaying. So I'll look for all the cases where I was displaying stuff, comment those out so that they don't start jobs that are streaming. Okay, I think we've got them all. I'm going to stop all the streaming jobs at this point. And I suppose the last thing I really ought to do is comment out where I deleted the directory, because obviously I don't want to start over from scratch every time I run the notebook. So I'm going to comment out command 14, where I was deleting the directory structure. I want to keep the directory here so that this can truly be a notebook now, that when I run this notebook, it'll update all the tables exactly once and then continue on. So now I'm able to do run all. It's going to run all of this one time and then complete. And I could launch a cluster once an hour or once a day to do those updates. And I've now got the best of batch, which is that I don't have to have my cluster always running, with the best of streaming. There it is. It finished. You see my job is completed. It no longer is running anything. I've gone all the way to the bottom of my notebook. I suppose there was probably one more cell at the bottom of the notebook I should have commented out. Oh, good, it didn't get this far, where I tell it to stop the streams. And I'm able to do really good insights and run this now as a nightly batch job. So I just go back to my job screen. I look for my newly created one that I created. And it's scheduled to run once a day, and it will run that notebook and update the tables. So now it's a batch job that's using streaming to only process what's new. Super duper powerful. My cluster is able to shut down in between streaming intervals this way. And obviously, I can also do really clever plots and exploratory data analysis on that gold table. So that gold table is available to me even when my streaming jobs aren't running. I'm able to read that gold table. It's just the latest known state of the data. And I could view people's average heart rate as it varies by day. So this is a good opportunity now for me to stop and look for questions. And I'm also interested in any comments you want to throw into the chat about how effective that demo was. And let me know what you think, if that was really helpful in seeing how you can use streaming with Delta to keep a data warehouse that's always up to date, and you don't have to use the Lambda architecture. Arnab mentioned he actually uses Azure Data Factory to trigger jobs in Databricks. You can absolutely do that. In which case, when you trigger a job in Azure Data Factory, it's able to call the jobs API to launch jobs that you've set up here in the jobs tab. And now Azure Data Factory can be driving and orchestrating that process, which is really cool. Somebody else mentioned this is similar to streaming analytics in Azure. And which is more expensive? So we really believe that you get a lot of cost savings by using Databricks. So there is some duplication and some overlap between what you can do with Stream Analytics in Azure and what you can do with Databricks. What's really cool is that either one of those two can be launched from Azure Data Factory to orchestrate the jobs. So we would encourage you to do a trial with Databricks. We believe we could save you some money, but we certainly, Microsoft actually bundles Databricks as a first-party service in Azure. So Microsoft is going to be happy if you're using streaming analytics. They're going to be happy if you're using Azure Databricks. They've got multiple options inside of Azure. And to really get down to which is better, we would get into what exactly are the features you're using. We love it when people use Azure Databricks because you have the high performance and high scalability. Let's see here. I certainly don't want to upset Microsoft by telling you that we're always better. There's cases where streaming analytics definitely has some great integration with other Azure products. Let's see here. What else? Can we access a Delta table when the cluster is off? Is a question from Nimesh. So right now I do have a cluster up and running, but I have no streaming jobs, and I'm able to query the Delta table. But I do need something to query that Delta table. So the Delta table is out there on S3 right now. So I could use a different tool to query S3. Like I could be using Athena or Presto to be querying S3. and not using Databricks, in which case my cluster could be turned off and I would still be able to query. Because at the end of the day, the files are on disk and you're allowed to query that disk. But if you want to query it using Spark, you do need a cluster. And one of the things I'm going to show you tomorrow in webinar session part 4 is how you could connect Tableau to a Databricks cluster so that Tableau is sending SQL queries to Databricks to then do the visualizations and have it execute and read those tables. And then we're also going to do machine learning tomorrow. Somebody else asked about certifications. So with this training, what you get access to is just the self-paced course materials. Databricks does actually offer certification tests that you can take. So if you go to academy.databricks.com, you can find some good certification tests that you can take, and we're going to be producing new certifications and newer certifications over time as well on different topics. All right, I think we have hit 12 o'clock. Let me see if there's one last question before we go. Looking at our list of questions. Somebody asked if there's an easier way to orchestrate this flow from bronze to silver to gold. And there is. We are actually coming up with a declarative way. You can even use a graphical tool to draw that orchestration. It's a new product coming out called Delta Pipelines. So stay tuned for announcements on Delta Pipelines this year. And it's going to make it even easier to describe declaratively your flow from bronze to silver to gold. It's doing the same type of work underneath, but it gives you a new syntax for doing it. You'll even be able to do it graphically. If you talk to our sales reps, make sure you ask them about Delta Pipelines. All right, so that was our last question. Kayla, I'm going to pass it back to you, and we can call it the end of today's webinar, and we look forward to seeing you again for part 4, where we're going to do business intelligence and machine learning.